So we're talking about multi-unit growth factors and partial unit growth factors. And that's what we worked on last time. So these are some questions about that. So a population of insects quadruples every 6 months. C is the 1 month growth factor. Okay, so let's just write that. So C is a 1 month growth factor. And we're quadrupling every 6 months. So now, which of the following are equivalent or equal to the 6 month growth factor? So first of all, we're quadrupling every 6 months. What does quadrupling mean? Times 4, right? So every 6 months, the population is times 4. Well, that's exactly what the 6 months growth, that's what the growth factor is. It would mean that you'd multiply by 4 every 6 months. That's our meaning for a 6 month growth factor. So certainly 4 is one of the answers. Multiply by 4 every 6 months. So now, there's other answers that have C's in them. So if C is the 1 month growth factor, then what is the 6 month growth factor? In 6 months, we will multiply by C every month. So is it 6C? No, what is it? C to the 6th. C to the 6th. Where's that? There it is. So for me, it was E and F. So C to the 6th is a 6 month growth factor, but likewise 4 is because we're quadrupling every 6 months. Does it make sense? So those two are equal. And that allows us to solve for the 1 month growth factor. So C to the 6th equals 4 because they're both the multiplier on the output that will give you the output 6 months later or 6 input units later, right? They're both multipliers on the output, and so therefore the 1 month growth factor is 4 to the 1/6. Took the 6th root of each. So that's our 1 month growth factor, 4 to the 1/6. Remember, so again, you can put in expressions. You can let WebWork be your calculator. Let WebWork be your calculator. It's really useful, especially when you enter into this fight over decimal places. That ends the fight right there. You win the fight. You win. Okay? You just put in an expression and you don't have to, and you're the victor. Okay. Find the 1 year growth factor. So 1 year. This was 1 month. So this is what we multiplied by every month. So how many times would we multiply by that every year? 12. So how do we express then the one number that would do that 12 times? 4 to the 1/6. There's our 1 month. So over the course of the year, what do we end up multiplying by? That's what we're asking. One day. So now we want to think about, I guess this is a hint here. Consider carefully where we want to get this 1 day growth factor from. Do we want to get it from 1 month? Or do we want to get it from 1 year? So there's a problem with getting it from the 1 month. What is it? Yeah. Yeah, so you might think you're going to do 1/30th to the 1/30th, but some months have 31. We know February has 28. So year would be more accurate. So we're going to take the 1 year growth factor. So I'll do parentheses, and I'll just copy and paste my answer from C. The 1/30th it did? Yeah. Because it's probably, decimal is probably close enough. Like it just, the decimal version is close enough. But this is a better way to do it because of that. But yeah, we want to do to the what? If we've got the 1 year and we want the 1 day, 1 over 365. So look at this daily growth factor. It's the result of building from all these other growth factors, right? What's the first growth factor we see there? 4. Quadruples every 6 months. So just 4 is the 6th month. We take it to the 1/6th, we get the 1 month. Take that to the 12th, we get the 1 year growth factor. Take that to the 1/365th. 1 day. So this expression is nice because you can see all those growth factors how we built one from the next. Okay.
So either the actual numerical number or that would be
Yeah. So, but the risk you have with if you do your calculator, the risk you have is you're gonna put in a decimal approximation, and so what is kind of particular in certain situations about how many decimal places are required, and so then well, so there's both, because this is exact, and this reflects that you built it. But then the other one, like, what if we wanted the 1 day percent change? Then we need to get the decimal approximation to pull off that percent change. So both are important. Green bar. Got it. Okay, questions on... And then remember that if you've forgotten, remember answer preview can help you give you information without wasting attempt, right? It gives you a nice visual of your answers. Sometimes it gives you a clue, like it'll give you some kind of error message before you've even wasted an attempt, and that could give you feedback by saving an attempt. So the preview button is really helpful, okay? Don't forget the preview button. Okay, what was the next one? 8. What is this page? There it is. Okay, number 8. Okay, really important problem. So they give us some particular inputs and corresponding outputs. There's no context involved here, but we have input as x, output as f of x, right? So initial value. The initial value is 768, right? No, okay, so you need the initial value corresponds to the input of 0. So we're going to need to do something to get this initial value. Actually, to get the initial value, we're going to need the 1 unit decay factor. So let's find that first. Let's do B first. So what decay factor is the easiest one to find first here? Notice that input is increasing by 3. So the most direct, the first decay factor that we can get most easily is the 3 unit growth factor. And otherwise, what do we multiply the output at 1 by to get the output at 4? That will be the 3 unit growth factor. So how do we find that multiplier? With that multiplier, that would take us from 768 to 576. And hopefully by now we know that's 576 divided by 768. So 576 over 768 is going to be our 1 unit decay factor. Okay? So now, that's the 3. Sorry, right, exactly. That's the 3. And let's actually, I want to get, yeah. This is the 3 unit decay factor. We want the 1 unit decay factor. Also 3 unit decay factor we can put down here. So we got that. So the order of the questions here is, you recognize that it's quite out of order from how you would approach this. That's okay. We can handle it, right? So we do that first. So what about the 1 unit decay factor? Take the 3 unit decay factor and divide by 3, right? Kennedy. Take the 3 unit and divide by 3 to get the 1 unit. Is that right? What do we do instead? Yep, so we saw, we've kind of worked that out several times, why that works. And we earned our right to do this. Just say, oh, we know that if you've got a 3 unit decay factor, the 1 unit decay factor will be the 3 unit the 1 to the 1/3 power, or the 1/3 root of the 3-unit decay factor. Okay, so now to get the percent change, let's get some good approximations here. So get both those percent changes. Where am I? Here? Yes. So 576 divided by 768. Oh, look at that. Nice round number. 0.75, and then 0.75 to the 1/3. 0.90, let's use 0.9086. I'll write it over here. So we got 0.75 and 0.9086. So this is our 1-unit decay factor. How are we going to get the 1-unit percent change? The 1-unit percent change? Is it around 90%, the percent change? No, that 0.9, that's a decay factor. So when you multiply by a decay factor, it gives you how much that you retain, keep, what remains. Okay? So we want to do 1 minus that. No, not that. There we go. So 1 minus that will give us the percent decrease. The percent decrease looks like 9.14. We'll do 4. 9.144. 9.144% decrease, or negative 9.144% change. Right? If you call it decrease, it's positive. If you call it change, it's negative. Okay, so 1 unit percent change was, so percent change, there's want change, so we're going to go negative 9.144, and then the 1/4. All right, so we'll do that later. We'll go back and get the initial value. So now the initial value is that value of the function when x equals 0. So there's different ways to figure this out, but one way to do it is to look at what we've got at 1 and think backwards. We need to move back 1 unit. So how can we go back 1 unit from 768? Divide by the 1 unit growth factor. So I can come up here and say 768 divided by my 1 unit decay factor. And that will take me back 1 unit. So I'll just take this whole thing. And I'll do parentheses, paste, 1 parentheses, and let's use preview. So I just want to show you the preview thing. So here's my 1 unit decay factor, and then I'm taking the output at 1, and instead of multiplying, I'm dividing by, so it takes me back 1 unit to 0. And so that's my, whatever that is, 845.293 will be my initial value, or the output when the input is 0. Everything else looks good. So even in the preview, you can let it be your calculator and give you decimal approximations with the preview instead of using a calculator if you prefer that. So the preview is really valuable. Don't forget it's there. All right, the 1/4 unit decay factor is going to be the 1 unit decay factor raised to the 1/4. Function definition. So now x is the input. So x, which growth factor are we going to use? So let's go back and get that. I'm going to do the preview and pull off this. I don't want to write that expression for the 845.293 is my initial value. 845.293. I just want to use that because this is a little too messy for the function. All right, so then we're going to have something to the x. So the question is, we've got all these decay factors flying around. Which one are we going to use if my input is x, according to this table? Yeah, so x is just increases by 1 unit at a time. Every time you increase x by 1, you move ahead 1 unit. So we're going to use the 1 unit decay factor. And I'll just copy and paste that. So copy, paste. So initial value times the 1 unit decay factor to the x. Green bar. Got it. Any questions on that one? Anybody have a question? Did that help? Is that helpful? So I think you got stuff like this on your quiz. Okay, getting these partial unit growth factor, decay factors and growth factors, and finding percent change, setting up the function, all super important.
Question.
Please.
Okay, so what if you're not giving any of that information, like the initial value? What would you say would be the verbiage? Would you just throw in another variable there? Like if you weren't given the value. So
am I given the table?
Okay, so you're not given the table.
No table.
Just the verbiage that table reflects. So you don't have the initial value, but you do know what the 1-day growth factor is.
Okay. Yeah, so you would it would be like A. Usually we use A for that. So if all you know is the 1-day growth factor, but you don't have any one output value, then it would just be A 1-day growth factor to the x. And then, so yeah. So the fact that we have at least one output value here is how we can generate the decay factors and get our initial value. But yeah, if you don't have any output values, then you won't be able to get the initial value. What else was there? Did I say the last one? What did I say? 12 or 13? Good, nice short one. All right. So we got one-hour decay factor. So we got decreases by 70% every 8 hours. What's the 8-hour decay factor? Then 0.3. We're going to keep 30% every 8 hours, so we're going to lose 70%. So 0.3 is the 8-hour decay factor. And then how do we get the 1-hour decay factor? We're going to take the 8-hour decay factor, and we want 1/8 amount of time. So it's to the 1/8. Okay, the 1-day percent change. Where is the 1-day percent change going to come from? It's going to come from one value and one value over only. It's going to come from the 1-day decay factor. Okay, and we're going to talk more about that today. So to get the 1-day percent change, we need the 1-day decay factor first. And so how are we going to get the 1-day decay factor? So we can go back here, 0.3 every 8 hours. So then what will we keep every 24 hours? 0.3 to the third. So if we multiply by 0.3 every 8 hours, then we're going to multiply by 0.3 3 times every 24 hours. So you're going to take that to the third. All right, and then so suppose you take 400 milligrams of ibuprofen. You're on a headache. So initial value 400. Your headache will return if the amount in your bloodstream goes below 100. So what we've got here is that 100. Is that an input or an output? That's an output. So we think about the graph. 400 is the initial value times 0. We're going to take 2 of these and get 400 milligrams. And then what's going to happen over time? Up or down? Down. Decay, right? Exponential growth, or in this case, exponential decay. And then at some point of time, that output's going to hit 100. And so that the answer will be input or output. We're looking for the input into a, say, ibuprofen function that will result in that output being 100. So this is the visual of that. So let's develop the function, and then I think we talked about last time, you're going to use your graphing calculator and do a graphical, use a graph to solve this. So if we'll call it, say, f of hours. So f of t equals initial value, 400. Do we have the 1 hour decay factor? Yes, 0.3 to the 1/8. So I think that's our function, the ibuprofen as a function of hours, right? As a function of hours. And so we need to know when, we want to know when the output is 100. And so we're going to graph this function. So graph it on your graphing calculator, and then use the graph to solve this. So y equals 400 times 0.3 to the 1/8 to the x. So I think that's our ibuprofen function. And we're going to graph this. Zoom out on the y-axis to see what's going on. There we go. And then I think using graphing y equals 100 and doing intersect. Okay, so there's here's this intersection point is what we want. And you got the intersect on your graphing calculator. This is giving me the point 100 comma 9.2 115, that's way too many decimal places, comma 100. So how many headache-free hours will it provide? So 9.22 hours. I'll try 9.221. Oh, what did I do wrong? Oh, it was percent change. I was doing the 1-day decay factor. So if we want percent change, we're going to take that thing, minus 1, and multiply it by 100 to get percent. So I have done a 1-day decay factor. Any questions on that one? Yes, please.
With the last one,
Yeah.
for C, couldn't you just put 100 equals that function that you created and solve that?
The problem is we don't have a way to solve for exponents yet.
Okay.
We're getting to that next. But if you've done that in another class, then yes. But we've got now that exponent is our unknown, and we haven't talked about how to get that algebraically. So that's what I told you last time. Whenever when you're given the output, you want the input, use a graphical approach. Or table, if you want to do the table in your calculator. Okay, last chance. Questions? Let's really focus in on percent change and how it works. Okay, so 1 unit growth factor or decay factor, we have normally called that B. And we know that we can easily get other growth factors. So if the 1 unit growth factor is B, what's the 16 unit growth factor? You should all know that that's B to the 16th. Over 16 units, you will have multiplied by B 16 times. B times B times B times B. And so we advance forward 16 units of input. It's like multiplying by B to the 16th to get the new output, right? Similarly, we got our partial unit growth factors. What's the 1/2 unit growth factor? If we wanted to just go 1/2 unit rather than a whole unit of input, we'd multiply by B to the 1/2, right? And if we wanted to advance only 1/5 of a unit, then we'd multiply the output by B to the 1/5. Similarly, B to the 1/8. Okay, so So growth. The point here is growth factors and decay factors are easily transferable. They're directly transferable. If you've got one, it's very easy to get another one just by manipulating the exponent, right? Okay, well then what about percent change? What about percent change? Okay, we know we can get the 1 unit percent change from the 1 unit growth factor. And similarly, we can get each individual percent change from its respective growth factor or decay factor. So growth factors have this easy transference from one to the other, but what about percent change? Do we have some kind of fast track to get from 1% change to another? Do we have it? So we want to investigate that. So suppose the 1 unit growth factor is 1.25. So I want you to find the 3 unit growth factor. Go, find the 3 unit growth factor if the 1 unit growth factor is 1.25. And what did you get? Anybody get something? 1.95, 1.25 cubed, right? 1.25 cubed, 1.95. Okay, so what's the 1 unit percent change in this scenario? What's the 1 unit percent change? The 1 unit percent change. 25%. Increase or decrease? Increase. Okay. 25. Are you taking video of class, Kennedy? Or picture? Oh, I see. Okay. I figured you were using it for something good. So. Got it. Got it. Okay. All right. Okay. So then, what about the 3 unit percent change? 95%, right? So, is that 3 times, is that 95% 3 times the 1 unit percent change? Clearly not. What's 3 times 25%? 75%. Okay, so this is a really clear example that percent change is not directly transferable. You can't take the 1 unit percent change and multiply it by 3 to get the 3 unit percent change. Likewise, you can't take the 1 unit percent change and multiply it by 16 to get the 16 unit percent change. Okay? Can't do it. So the question is, why? What's going on here? Why don't we get that? So let's investigate this. So we're going to talk about 25% increase per unit of x. And we'll just say that initial value is 100 to make it nice and easy. So if we increase by 25%, what will we have after 1 unit? If we increase by 25%. That should be an easy question. 25% of 100 is 25. If we increase by 25%, we'll increase by 25. Okay, so I want to put that on both here. So 3 times 25% is 75%. So let's just say, if we were saying that the 3 unit percent change should be 75%, then what would we have at the end of 3 units? How much would we have then? If we're reasoning that if the 1 unit percent increase is 25%, then the 3 unit percent increase must be 75%. Then what would our output value be at 3? 175. And what would it be at 2? So how in this scenario? Oh, okay. All right. How in this scenario is the output growing from unit to unit? How is it growing? If we're saying that 25% increase per unit of x means 75 over 3 units, what? Yeah, why is the constant rate of change? Good. It's increasing by how much? Additive or multiplicative growth? Additive growth. You're adding 25. So we took 25% the first unit, but then we held on to that amount of percent, and then we just kept adding it. And that's what would result in a 75% increase over 3 units. So by saying 25% increase for 1 unit results in 75% for 3 units, that's reasoning by constant rate of change. You just be adding that initial 25% every time. So that's why it doesn't work. So what's really happening? So this is not exponential growth. This is not 25% increase per unit of x. This is adding 25 to the output every time. So what is exponential growth? Truly, 25% increase per unit of x means what do we do to get the next output? Everyone should know this, not just James. Okay? What does 25% increase per unit of x mean we do on every output to get the next output? You're all thinking it, right? Multiply by 1.25, the growth factor. So that means I'm going to multiply this by 1.25. What do you get? Take 125 times 1.25 and tell me what you get. 166? 156.25. And then we saw that it was 95% increase. So this should be 195. 195 point what? 3. So what happens? Now we took 25% of 100 and it increased it by that much. But then what happened? We took 25% of 125, not 100. So that the amount of increase was bigger because we're taking 25% more of a bigger number than 100. So we got the 25% of the 100 plus another 25% of the new 25. And now what? Now we're going to get 25% of 100 plus 25% of 56.25. So what's happening? The percent increase is building not only on the initial value, but building on the amount of increase. So you get percent increase on top of percent increase. And that's why you get this larger, the total percent increase is 95% per 3 units, rather than 75%, which would just be adding 25 every time. So here, this is multiplying, and so the percent increase is not only of the 100, but of the amount, the higher amount that you get each time. And so then it has a compounding effect, right? It has like a snowballing effect. Okay, does that make sense? Any questions? Okay, so then if we have 1% change and we want another percent change, how are we going to get it? We don't have the direct transference. So if we have, for instance, if we know the 1 unit percent change is 2.5%, how are we going to get the 16 unit percent change? I'm giving you a nice visual here, right? How are you going to get from the 1 unit percent change to the 16 unit percent change? How are you going to get there? Stay on the road. You're just going to stay on the road. There's no road that goes right from here to here. But if we stay on the road, we can get there. So we're going to first find the 1 unit growth factor. Then we can find the 16 unit growth factor. Then we can find the 16 unit percent change. Right? Do it. Let's go. Find the 16 unit percent change. Okay, Marlene. How'd you do? Did you get it? Can you just, did you get some of it? Can you talk me through it? So if we're here at the 1 unit percent change, how are we going to get and find the 16 unit percent change? It's going to be through what? Through the growth factor. So which growth factor are we going to get first? Right. So if we have 2.5% increase, what's the corresponding growth factor to 2.5% increase? 1.025. And now, remember, growth factor is easily transferable. That means we can get the 16 unit growth factor easily. How would we do it? Yeah. And that's 1.48. 16 unit percent change. %. Is that what you guys got? Rest of you? Makes sense. Another practice problem. Okay, 3 unit percent change is 79%. What's the 1/2 unit percent change? Go. Nancy, right? Talk me through it. Did you get it? Just get me started. So we'll work it through together. What first? No. So the whole point is, the whole point is we need to stay on the road to get from here to here. So what's our first stop in our journey from 3 unit percent change to 1/2 unit percent change? What's our first stop? To do what? 1 unit growth factor? There's another stop before that. See, those aren't connected, right? So there's not an easy way to get right from 3 unit percent change to 1 unit growth factor. 3 unit growth factor, right? Which is going to be what? If we have 79% increase, what's the corresponding growth factor? Not sure? We're increasing by 79%. What are we multiplying by? By 3? What's your name right next to her again? Yeah. Brianna? Tell me, what's the 3 unit growth factor? Do you know? Where's the 0.025 coming from? No, our 3 unit percent change is 70. This is a new problem. The 3 unit percent change is 79%. So what's the corresponding growth factor for 79% increase? 1.79. 0.79 would be 7.9. Okay? All right, now we're on the growth factor lane, right? So where do we want to go next? So if you can go right to 1/2, that's fine, but we can stop at 1 unit growth factor because that's kind of the home base, right? Home base is the 1 unit growth factor, easy to find the rest. How will we get the 1 unit growth factor? Brighton.
You would do 1.79
to the 1/3? To the 1/3. That'd be our 1 unit, and then how would we get the 1/2 unit? That to the 1/2, right? You take the 1 unit to the 1/2. And now let's get a value for that. So going directly from the 3 unit to the 1/2 unit would be 1.79 to the 1/6. So if you that's fine. If you want to go right from here to here, you're going to take that 1.79 to the 1/6. because 1/2 is 1/6 as much as 3. And we see that right there in the exponent. 1/3 times 1/2 would be 1/6. What is our value of our 1/2 unit growth factor? 1 point? Nice and loud. 1, 0. 1, 9. Is this right? Percent, 1/2 unit percent change. $10.19%. Questions? Does it make sense? Okay, so now let's do decay. Decay is a little harder, right? So decay, there's more to it. So if the 1/2 unit percent change is negative 1.8%, so we're decaying by 1.8% per 1/5 unit. Find the 10 unit percent change. It's a little harder, but we should be able to do it. Okay, Yufan, you're up. Process. Let's go one step at a time. Okay, how'd you get that? Okay. 98.2. Okay, so the 1/5 unit growth factor is? He wants 0.982. The amount we keep every 1/5 unit. The portion that we keep. Is this right? Keep going. To the 5? So we're going to take the 1/5 unit growth factor to the 5th to get the 1 unit. Good. To the 10th. So if I take it to the 5th and then to the 10th, it's like taking it to the 50th. So I take that whole thing to the 10th. That'd be the same as taking the 0.92 to the 50th. Yeah, please.
I'm not sure really how you got that 98.
Okay, so this is percent decrease. How do we get a decay factor from a percent decrease? So this is how much we lose, and remember the decay factor is how much we keep. So if we're losing 1.8%, how much are we keeping? How would you get how much we're keeping if we're losing 1.8%? What's that? You're going to take everyone 100%, right? You're going to take 100% minus 1.8, and you're going to get 98.2% that's kept every 1/5 unit. And that's our multiplier, 0.982.
Okay. All right.
Okay. What is 0.982 to the 50th? One four? Is this right? Did I hear that right? 10 unit percent change now. So we got, this is, again, how much are we keeping? We're keeping 40.325% kept every 10 units. So yeah, we got to subtract 1. And we're going to get right, so then that's how much we are losing, which is what percent? 59.675% lost. Or we could say negative 59% change, percent change. And that's the answer. Okay, last one. Negative 34% half unit change. What's the 1/8 unit change if the half unit percent change is negative 34%? So write that down. I need to get to the attendance spreadsheet. So write down the problem. Negative 34, this is what you need to write down. Negative 34 is the half unit percent change. What's the 1/8 unit percent change? Those are the three things you need to write down. Because I need to take this screen away. Negative 34% is the 1/2 unit. What's the 1/8 unit percent change? Got it? Andy? What was the answer? What was the percent change for 1/8 unit? Nice enough? 9.8% decrease. Is that what you got? If you didn't get it, you have to stay and get it right. Kyler?